Hi guys, we are continuing chapter 14 and reaction rates, and we are talking about the order of the reaction. And remember we said that the order of the reaction, like when we write our rate law, rate is equal to K, like a constant, times the concentration of the reactants raised to some power, and that power is my order. And remember we said that power, the order, represents the dependency of the rate on the concentration. So we said if it's zero order, then the rate is not dependent on the concentration. So if I double the concentration, nothing happens to the rate. If that is first order, then the rate varies directly with the reactant concentration. So if I double my concentration, my rate doubles. If it's second order, then the rate will vary with the square of the reactant concentration. So if I double my concentration, I quadruple my rate. Or if I triple my concentration, I increase my rate by 9 times, and so on. So that X, Y, and Z are the order, and the order tells you the dependency of the rate on the concentration. So we said that there are 3 methods to, there we are. I'll find it. Here you go. There are 3 methods to determine what that order is. And the first method we talked about is looking at mechanism and knowing what the rate determining step is, and from there figuring out what the order is. The second method is by data inspection. So what you do is you carry out your same experiment several times, and you vary the concentration of your reactants, time the experiment, and look at your rates and see how the rates change based on the changes in the concentration. So let's look at this experiment here. We have 2NO plus 2H2 yields H2 plus yields N2 plus 2H2O. We want to determine what the rate law is. So we know that the rate is going to be the concentration of my reactants raised to some power X and Y. We don't know what X and Y are. Again, those are the orders with respect to NO and H2. So let's say we want to know what X is. So the order with respect to NO. So what you do is you look at 2 experiments where the NO changes, but the other reactants don't. So we want to look at 2 experiments where the H2 is constant, but the NO changes. So I'm going to pick, let's say, experiments 1 and 2, because the NO is changing, but the H2 remains the same. You could also pick 1 and 3 or 2 and 3, because in all of these, this is held constant and these are changing. I picked 1 and 2 because I see that my reactant concentration doubles here, so my math is a little bit easier. So I look at these are the same. This is doubling. So I look here and see, oh, this is 4 times. So I try to express this 4 as 2 to some power. So I try to express my change in the rate as the change in the concentration to some power. So I see my concentration is doubled, so 4 is 2 squared. That is my order. It is second order. Because when I double my concentration, my rate quadruples. So that tells me that it's second order. So experiments 1 and 2, concentration of the NO doubles, the rate is 4 times, so I know that it's NO to the second power. That's second order with respect to the NO. Now let's look at the H2 and what Y would be. So if I want to look at H2, I want to look at 2 experiments where I'm changing H2, but my NO is held constant. So it looks like NO is held constant in experiments 4, 5, and 6. So I want to pick 2 of these experiments. It doesn't matter which one. Just for simplicity, I'm going to pick experiments 4 and 5. These are the same. This one looks like a double, and so this one looks like I'm also doubling it. So what I do is I look at the change in the rate and I express this as the change in the concentration to some power. So 2 is equal to 2 to the first power, and so that tells me that it is first order with respect to the hydrogen. So experiments 4 and 5, I'm doubling my concentration of H2. The rate is also doubled, so that looks like it's first order with respect to my hydrogen. So my rate law then is going to be rate is equal to a constant times the concentration of NO to the second power times the concentration of H2 to the first power. So I inspected the data and saw how the rate changes based on the changes in the concentration. What is the overall order of the reaction? So the overall order of the reaction means if I add up the order with respect to all my reactants together, so this is second order with respect to NO, and first order with respect to the H2, that's, if you don't have anything there, that's a 1, right? And so it is third order overall, or order is equal to 3. Lastly here, it's asking me to find K. See how there's K is a constant in my equation here? Well, what is that K equal to here? So sometimes they'll tell you find K in a certain experiment. Sometimes they'll just give you the option. So you can really pick any experiment. So pick any of the experiments since they don't tell you which one to use. So let's pick experiment 3. So this one right here. I know that my rate is equal to K times the concentration of NO2 squared times the concentration of H2. So I'm going to say my rate, which is 0.018 molar per second, and I'm just getting that number from right here, and the units are moles per liter, which is molar over second, is equal to K. That's what I'm solving for. In experiment 3, the concentration of the NO is 0.003 molar, and I square that times concentration of H2, which is 0.004 molar, and that's to the first power. So I solve for K, and I got my K to be 5 times 10 to the 5th, and let's look at our units together. So I'm taking, I'm going to use a different color here. This is moles per second is equal to K times molar squared times molar, right? So if I'm solving for K, I can say K is equal to the molar per second, and then I move these, they go to the bottom, so molar squared times molar. So I end up with my units as 1 over molar squared times second. And so that's my answer. Yeah, the units for K are important, and there's different ways to do it. I just cancel my units to figure out what units I get, but we will look at the units for first, second, and third order. Okay, let's do another one. So there's my reaction again, and I want to know what the rate law is. So I know that the rate law is going to be rate is equal to K times the concentration of H plus to some power times the concentration of the bromate ion to some power times the concentration of the bromide ion to some power. And I want to know what X, Y, and Z are. So we are going to look at these experiments and we're going to try to figure out what X, Y, and Z are going to be. And in here, the numbers are relatively easy, and in the previous example, they were also relatively easy, but I'm going to write it out a little bit more mathematically to show you another way. Instead of writing it in words, this doubles, and so this triples, and so on. We'll show a little bit more math. So I'm going to start with my H plus, maybe. Yeah, let's do that. And I want to look at two reactions where my H plus is changing, but my other two are remaining constant. So which two would you look at? I think if you look at experiments 1 and 4, looks like my bromate and my bromide are remaining the same, but my H plus is changing. So I'm going to pick experiments 1 and 4. So to show my work, what I'm going to do is I'm going to look at the change in concentration in experiment 4 versus 1 for the H plus. And I'm going to say, so here's my experiments right there. So I'm going to say 0.20 molar for experiment 4 over 0.10 molar for experiment 1, which gives me 2. I chose to do 4 over 1 just so the numbers are a little bit easier, so it's 2 as opposed to half, but it's totally up to you. So you do the same thing for the rates. So rate of 4 over rate of 1. And so rate of 4 is 3.2 times 10 to the negative third molar per second. This one is 8.0 times 10 to the negative fourth molar per second. And so this gives me 4. So then I express my 4 as equal to 2 to some power, because my change in concentration was double. So this is 2 to the second, so it is second order with respect to the H plus. Okay, now I'm going to look at bromate. So I want to pick two experiments where my bromate changes, but my H plus and my, just trying to erase this so it's just a little bit easier for us to look. So I want to look at two experiments where my bromate is changing, but my other two are remaining constant. So which two experiments would you pick for the bromate? Well, I think I would pick experiments maybe 1 and 2, because for experiments 1 and 2, my bromate is changing, but if you look at the bromide and the H plus, they are remaining the same. So I'm going to go with experiment 2 over experiment 1. So my bromate ion concentration in experiment 2 over my bromate ion concentration for experiment 1 is 0.20 molar over 0.10 molar, which is equal to 2. Let's look at the rates for the same two experiments. So rate 2 is 1.6 times 10 to the negative third molar per second. Rate 1 is 8.0 times 10 to the negative third molar per second. That is equal to 2. So then you express the change in your rates as the change in the concentration to some power. So this is the same thing as 2 to the first power, and so it is first order with respect to the bromate ion concentration. Okay, let's now look at the bromide ion concentration. So we're going to pick two experiments where the bromide is changing, but the bromate and the H plus are remaining the same. I think if we pick experiments 2 and 3, that would get us there. So experiments 2 and 3, my bromide is changing, but my other two are remaining the same. So I'm going to do the same thing. My bromide ion concentration for experiment 3 over my bromide ion concentration for experiment 2 is 0.2 molar over 0.1 molar, which is equal to 2. Then I compare my rates for the same two experiments. So 3.2 times 10 to the negative third molar per second over 1.6 times 10 to the negative third molar per second. That looks like it's equal to 2. So again, I express my change in concentration as my change in rate as my change in concentration to some power. So it's the same thing as 2 to the first. So first order with respect to the bromide ion concentration. So then my overall rate law is going to be rate is equal to K times the concentration of the H plus squared times the concentration of the BrO3 minus to the first power times the concentration of the Br minus to the first power. And this is my answer. So you can use it mathematically like this, or you can use words to kind of express it kind of like that. Okay, next we want to find the value for K in reaction 2. So we're going to look at reaction 2. And reaction 2 right here. Sorry, it's kind of messy. But I'm going to say rate, I'm going to rewrite this, K times the concentration of H plus squared times the BrO3 minus times the Br minus. My rate for experiment 2 is 1.6 times 10 to the negative third molar per second is equal to K times the concentration of H plus. I'll make sure I'm writing it correctly here. The concentration of H plus is 0.1 molar. But that's squared times the concentration of the bromate. The bromate is the first one, so it's 0.20 molar. Times the concentration of the bromide, which is 0.10 molar. And I solve for K. I got 8.0 as my answer. Let's look at the units. So this is molar per second times K. This is molar squared times molars times molar. And so this is really molar to the fourth, right? So let's see. So then I can say K is equal to molar over second, and I move these to the bottom here. So this crosses, this becomes third. So it is 1 over molar cubed seconds, and that is my answer. Let's do one more problem. It says the rate at which 0.1 molar CH3CHO decomposes is of the second order and is at a constant rate of 0.18 molar per second. What would be the rate if a 0.40 molar solution were used? So let's think about this. I'm given that it is second order. So automatically I can say, well, the rate is equal to K times the concentration of my reactant, which is this, squared. I also know that the rate of 10th molar is 0.18 molar per second. So I know that the rate is 0.18 molar per second if this was 10th molar, right? So what I could do is I could solve for what K is and then plug it back in here with 0.4 molar to find what the rate is. So let's do that. So if I do this, I'm going to get K to be 18, and the units should be molar per second over molar squared, so it would be 1/molar second. And then I could plug it back in here. Squared. So rate is equal to my K, which is 18, times 0.040 molar squared. And I can solve for the rate. And it ends up being 2.88 molar per second. And that is my answer.